Tonight, we follow the story of why Earth shines like a gentle blue star, a world wrapped in light, air, and oceans that glow softly in the darkness of space. Welcome to the Orbit for Sleep channel. Let us follow the orbit of science and drift gently towards sleep. When we look at Earth from space, the first thing that catches the eye is its gentle blue glow. It almost looks like a faint star wrapped in a soft veil of light. This glow is not a trick of the camera or a poetic exaggeration. It comes from a precise interaction between sunlight and the thin shell of air surrounding the planet. The process is simple, but its result is one of the most recognizable signatures of our world. Sunlight arrives at Earth as a blend of all colors. Each color travels as a different wavelength, and blue light has one of the shortest. Short wavelengths are easily disturbed, like dust stirred by a passing breeze. As sunlight enters the atmosphere, it meets billions of nitrogen and oxygen molecules. These molecules are tiny, so tiny that the short blue wavelengths bounce off them more strongly than the longer reds and yellows. This interaction is called Rayleigh scattering. In simple terms, Rayleigh scattering means that shorter wavelengths are scattered in every direction, much more than longer ones. Because blue light is scattered the most, it becomes the dominant color filling the sky. The effect is calm but continuous, like countless tiny ripples spreading outward in all directions. From the ground, we experience this scattering as the familiar blue sky. But from above, the perspective changes. Seen against the blackness of space, Earth's atmosphere becomes a glowing ribbon of blue, tracing the planet's curved edge. Astronomers often describe this thin line as one of the most delicate sites in the solar system, a fragile boundary where sunlight meets air. The oceans strengthen this impression. Water absorbs most wavelengths of light, but reflects small amounts of blue, adding depth and richness to the planet's color. Yet the atmosphere remains the main reason Earth shines the way it does. Without this constant scattering of blue light, the planet would look far dimmer and far less alive. This blue glow is not bright like a star, but soft and diffused. It gives Earth a peaceful presence in the cosmic darkness. A simple physical process, sunlight meeting molecules, creates a color that marks Earth across the vast distances of space. Sunlight is made of many colors, each with its own wavelength. Blue and violet have the shortest wavelengths, while red and orange have the longest. Short wavelengths travel in tight, rapid waves, almost like threads pulled taut. When this blended light enters Earth's atmosphere, it encounters nitrogen and oxygen molecules, particles much smaller than the wavelength of visible light. Because these air molecules are so tiny, they interact most strongly with short wavelengths. This selective interaction is called Rayleigh scattering. It describes a simple rule: the shorter the wavelength, the more it scatters. Blue light scatters about 4 times more than red light. Violet light scatters even more, but human eyes are less sensitive to it, and parts of the atmosphere absorb some of that violet. As a result, blue becomes the dominant, scattered color. Rayleigh scattering spreads blue light across the entire sky. The process is gentle but constant. Photons, tiny packets of light, bounce from molecule to molecule, shifting direction over and over. From the surface of Earth, these countless scatterings blend into a soft blue wash. The color has no single source point. It fills the sky evenly, like dye diffusing through clear water. When viewed from space, the effect looks different. Instead of filling the sky, scattered light forms a thin, luminous shell hugging the planet. This shell appears brightest when sunlight passes through it at a shallow angle, highlighting the upper atmosphere. Against the dark backdrop of space, this faint band of blue becomes one of Earth's defining features. Rayleigh scattering also changes throughout the day. When the sun is high, sunlight passes through a short path of atmosphere, allowing blue light to dominate. During sunrise and sunset, sunlight travels through a much thicker layer. Blue light scatters out before reaching the observer, leaving behind the longer wavelengths, reds and oranges that paint the horizon. This behavior is not unique to Earth, but Earth's specific mix of gases, pressure, and temperature makes the effect especially strong. Rayleigh scattering shapes how we perceive daylight, twilight, and the color of our atmosphere. It is a quiet, reliable process that reveals how light behaves when it meets the thin, fragile layer of air that protects our world. From the ground, the sky stretches above us as a wide blue dome. The color feels distant yet surrounding, like a soft canopy made of light. But from space, Earth's blue is different. It appears as a thin, concentrated band hugging the planet's edge, glowing against the black background. Both views come from the same physical process, scattering of sunlight in the atmosphere, but each perspective reveals a different part of that interaction. Standing on Earth's surface, we look through a dense layer of air. Sunlight enters this layer and scatters in all directions, with blue wavelengths spreading the most. Because this scattered blue comes from every direction above us, our eyes perceive it as the sky itself glowing. The light is diffused and gentle, forming a broad, uniform color. The sky appears bright because we are inside the scattering medium, surrounded by countless air molecules. In space, the situation changes completely. An observer outside the atmosphere sees the scattering from the side, not from within. Instead of a full dome, the scattered light forms a glowing ring around the planet. The atmosphere is extremely thin, less than 1% of Earth's radius. But sunlight passing through this thin edge scatters enough blue light to create a vivid line. Against the vacuum of space, this glow looks sharper and more intense, almost like a delicate outline drawn with light. This difference in perspective explains why Earth appears as a radiant blue sphere from orbit. Most of the planet's surface is covered by oceans, which absorb longer wavelengths and subtly reflect some blue, deepening the color we see. But the atmosphere remains a primary contributor. Without it, Earth would appear darker and more neutral, more like the moon. Another contrast comes from how our eyes adapt. On the ground, the sky seems bright because sunlight floods the atmosphere. In space, the darkness around the planet makes the blue edge appear more luminous. The human visual system amplifies contrast, making thin atmospheric scattering stand out dramatically. Together, these viewpoints reveal two complementary truths. From the ground, the sky forms an immersive ocean of blue. From space, the atmosphere becomes a glowing ribbon marking the boundary between Earth and the cosmos. Both visions arise from the same physics, seen from two very different vantage points. Earth's oceans cover more than 2/3 of the planet's surface, and they play a quiet but important role in shaping the blue appearance of our world. When sunlight reaches the ocean, water does not reflect all colors equally. Instead, water absorbs long wavelengths, reds, oranges, and yellows, much more efficiently than short wavelengths. Blue light, with its short wavelength, penetrates deeply into the water before it is absorbed. A small portion of this blue light is scattered back upward, giving the oceans their familiar color. Most of the sunlight that hits the ocean is actually absorbed, not reflected. This is why the sea can appear dark or nearly black when the sun is low or when the water is deep. Yet under the right conditions, clear skies, strong sunlight, and calm surfaces, the ocean reflects a soft hint of blue. The reflection is subtle, more like a faint shimmer than a mirror. The ocean's surface behaves like a gentle, flexible sheet, bending and shaping light as waves move. From space, this behavior becomes even more striking. The oceans absorb most incoming light, creating broad regions of deep blue that contrast with bright clouds and land masses. While the atmosphere is the main source of Earth's overall blue glow, the oceans add depth and saturation, reinforcing the planet's identity as a blue world. The interaction between sunlight and water also changes with angle. When viewed from above, light penetrates the surface and scatters from particles suspended in the water, producing rich blue tones. When viewed from the side, especially near the horizon, the ocean reflects more of the sky's blue light. This reflection ties the color of the sea and the color of the sky together, blending them into a continuous spectrum of blue that spans from the surface to the upper atmosphere. The transparency of water also contributes to this effect. Clear water absorbs almost everything except blue light. This is why, even deep underwater, the world gradually shifts to shades of blue as other wavelengths fade away. In this sense, the ocean acts not just as a surface, but as a filter that shapes the color of the planet. Together, these interactions create a subtle partnership. The sky scatters blue light downward, and the ocean reflects and returns it. This quiet exchange of light between air and water helps Earth present itself as a shimmering blue sphere when seen from far away, a planet where sunlight meets the sea in a balance of absorption and reflection. Even if Earth had no oceans, the planet would still appear bright from space. This brightness comes from clouds, snow, and ice features that reflect a large amount of sunlight back into space. Their reflective power is called albedo, a term that describes how much light a surface bounces away instead of absorbing. Clouds, fresh snow, and polar ice have some of the highest albedo values found on Earth. Clouds are made of tiny droplets and ice crystals suspended in the air. When sunlight enters a cloud, it meets millions of these particles. Each droplet scatters the incoming light in many directions. Unlike the selective scattering of blue wavelengths in the atmosphere, cloud droplets scatter all visible wavelengths almost equally. This is why clouds look white from the ground. From space, this scattering forms broad, bright patches that shine strongly against the darker land and sea. Snow and ice behave in a similar way. Fresh snow has an exceptionally high albedo because its surface is filled with countless tiny crystals, each acting like a reflective surface. When sunlight hits snow, most of the light is reflected rather than absorbed. Polar regions, covered in ice and snow for much of the year, contribute significantly to Earth's overall brightness. These regions send a strong signal of reflected sunlight into space, creating brilliant white caps at the top and bottom of the planet. Together, clouds and snow create a balance that maintains Earth's brightness. Clouds constantly shift, forming dynamic patterns of light. Snow and ice provide stable reflective surfaces that anchor the planet's luminous appearance. Even on days when the oceans appear dark or the sky is muted, these bright surfaces keep Earth glowing. From orbit, this mix of reflectivity stands out. The planet is not a uniform blue sphere, but a textured one. Deep oceans, glowing clouds, bright polar caps, and scattered land masses all contribute to a layered, shimmering appearance. While the atmosphere gives Earth its blue outline, clouds and snow ensure that much of the planet remains bright and visible. This reflective combination highlights a simple truth. Earth's color is not produced by a single source. Instead, it is a collaboration between air, water, and ice. Sunlight interacts with each component differently, creating a complex but harmonious visual signature that can be seen from across the solar system. Earth's atmosphere is not a single uniform shell. It is a series of layers, each with its own density, temperature, and behavior. These layers shape the way sunlight moves, scatters, and fades as it travels downward. The overall structure looks simple from a distance, a thin blue envelope around the planet. But up close, each region plays a different role in creating Earth's color. The lowest layer is the troposphere. This is where almost all weather occurs and where most of the air molecules are concentrated. Because it is so dense, the troposphere is responsible for the majority of Rayleigh scattering. Sunlight entering this layer meets countless nitrogen and oxygen molecules, causing blue light to scatter widely. This scattering fills the sky with color and softens the daylight that reaches the ground. Above the troposphere lies the stratosphere. The air here is thinner and colder, but contains the ozone layer, which absorbs harmful ultraviolet radiation. Although ozone plays only a small role in visible color, it helps filter high-energy wavelengths before they reach the lower atmosphere. When sunlight passes through the stratosphere at shallow angles, such as during sunrise or sunset, the scattered light can interact with ozone, adding subtle tints to twilight. Farther up is the mesosphere and then the thermosphere. These layers contain very few molecules compared to the lower atmosphere, but they extend over vast heights. Sunlight passing through these upper regions scatters only faintly. Yet this faint scattering becomes visible from space as a thin blue arc outlining Earth's curve. The higher the layer, the sharper and more delicate this edge appears. The exosphere forms the final boundary between the atmosphere and outer space. It is extremely thin, with atoms drifting far apart. Scattering here is minimal, but the transition from the last traces of air to the vacuum of space creates the visual contrast that makes Earth's blue rim stand out so clearly. Together, these layers determine how sunlight evolves from a direct beam to a diffuse glow. The dense lower atmosphere creates the blue sky we see from the surface. The thin upper layers create the glowing edge we see from orbit. Each layer filters, bends, and scatters light in a slightly different way, forming a smooth gradient of brightness that wraps around the planet. This layered structure is not visibly separated to the human eye, yet its effects are unmistakable. The way Earth shines soft, blue, and luminous is the result of sunlight passing through a vertically stacked series of invisible boundaries. Light, air, and height combine to create the planet's quiet optical signature. Earth's atmosphere is not made only of gases. It also contains tiny particles called aerosols, dust, sea salt, smoke, volcanic ash, and even microscopic fragments. Creating a process known as Mie scattering. Mie scattering does not favor short wavelengths. Instead, it scatters all visible wavelengths more evenly. When aerosols fill the atmosphere, the strong preference for blue light weakens. The sky becomes paler, the horizon turns hazy, and Earth's overall color looks softer and less saturated. From orbit, regions with heavy aerosol content can appear almost gray or whitish, especially during large dust storms or seasonal wildfire events. Dust from deserts can travel across entire oceans. For example, Sahara dust frequently crosses the Atlantic, forming enormous plumes that reflect sunlight and brighten parts of the atmosphere. These dust layers scatter light forward more than outward, creating a muted glow that stretches horizontally. The effect is subtle but noticeable from space, where these plumes appear as thin, slightly opaque veils over the deep blue ocean. Sea salt aerosols, formed by breaking waves, behave differently. They tend to be larger and scatter light more efficiently. When winds lift them into the air, they increase the brightness of the lower atmosphere, especially near coastlines. Smoke from forest fires and pollution from human activity can dim the sky, absorbing some wavelengths and scattering others. These pollutants often give the atmosphere a brownish or hazy tint, reducing the clarity of Earth's blue outline. Volcanic eruptions add another layer of complexity. They can inject ash and sulfur compounds high into the stratosphere, where the particles remain for months or even years. These particles scatter sunlight strongly, often creating vivid sunsets and altering Earth's reflectivity. From space, volcanic aerosols can make large areas of the atmosphere appear pale, silvery, or slightly tinted. Despite these variations, Earth's overall blue tone remains because the atmosphere is still dominated by nitrogen and oxygen molecules. Aerosols modify the color, but rarely overwhelm it. Their presence adds texture to the planet's appearance, a shifting blend of clear and hazy regions that reflect the changing conditions of the surface below. These particles reveal something important about Earth's atmosphere. It is dynamic, constantly shaped by winds, seasons, weather, and life. The planet's blue glow is not fixed. It brightens, fades, and changes subtly depending on what floats in the air, giving Earth a living, breathing quality when viewed from above. Water vapor is one of the most delicate components of Earth's atmosphere. It is invisible, constantly moving, and always changing. Yet its presence has a subtle effect on how sunlight spreads through the air. While nitrogen and oxygen are responsible for the strong scattering that makes Earth blue, water vapor adds softness like a gentle filter that smooths the light passing through it. Water vapor absorbs certain wavelengths of sunlight, especially in the infrared part of the spectrum. This absorption does not change the dominant blue color we see, but it reduces the overall intensity of scattered light. As a result, the sky can appear slightly dimmer or more muted when humidity is high. Instead of a sharp, vivid blue, the sky forms a quieter tone, similar to watercolor spreading across paper. In addition to absorbing some wavelengths, water vapor also contributes to subtle scattering. The molecules are larger than nitrogen and oxygen, but much smaller than aerosols, placing them in a transitional zone where their optical behavior gently blends both effects. This middle-scale scattering softens brightness without strongly altering color. It creates the smooth gradients that often appear near the horizon, where the air contains more moisture. As sunlight enters humid air, each photon interacts with moving clusters of water molecules. These interactions blur the light slightly, making the atmosphere look less crisp. On warm, moist days, the horizon can appear hazy even without dust or pollution. From space, regions with high humidity may look slightly less blue and slightly more diffuse, giving Earth a soft-edged appearance. Water vapor also plays a role in forming clouds, which further modify Earth's shine. Before droplets become visible clouds, they begin as invisible vapor rising from oceans, forests, and lakes. This invisible phase influences light long before it condenses into reflective white cloud tops. It shapes the transition between clear blue skies and bright cloud layers, creating smooth, gradual shifts in brightness. The distribution of water vapor is uneven, changing with weather patterns, seasons, and geography. Tropical regions typically show stronger softening effects, while dry deserts reveal sharper blue tones. This variation adds texture to the way Earth appears from orbit. Some regions glow with deep blue clarity, while others look gentle and subdued. Although water vapor does not define Earth's blue color, it fine-tunes it. It adjusts the brightness and smoothness of scattered light, giving the planet a calm, slightly diffused glow. In this way, water vapor acts like a natural lens, quietly shaping the look of Earth's atmosphere without drawing attention to itself. Water vapor is one of the most delicate components of Earth's atmosphere. It is invisible, constantly moving, and always changing. Yet its presence has a subtle effect on how sunlight spreads through the air. While nitrogen and oxygen are responsible for the strong scattering that makes Earth blue, water vapor adds softness like a gentle filter that smooths the light passing through it. Water vapor absorbs certain wavelengths of sunlight, especially in the infrared part of the spectrum. This absorption does not change the dominant blue color we see, but it reduces the overall intensity of scattered light. As a result, the sky can appear slightly dimmer or more muted when humidity is high. Instead of a sharp, vivid blue, the sky forms a quieter tone, similar to watercolor spreading across paper. In addition to absorbing some wavelengths, water vapor also contributes to subtle scattering. The molecules are larger than nitrogen and oxygen, but much smaller than aerosols, placing them in a transitional zone where their optical behavior gently blends both effects. This middle-scale scattering softens brightness without strongly altering color. It creates the smooth gradients that often appear near the horizon, where the air contains more moisture. As sunlight enters humid air, each photon interacts with moving clusters of water molecules. These interactions blur the light slightly, making the atmosphere look less crisp. On warm, moist days, the horizon can appear hazy even without dust or pollution. From space, regions with high humidity may look slightly less blue and slightly more diffuse, giving Earth a soft-edged appearance. Water vapor also plays a role in forming clouds, which further modify Earth's shine. Before droplets become visible clouds, they begin as invisible vapor rising from oceans, forests, and lakes. This invisible phase influences light long before it condenses into reflective white cloud tops. It shapes the transition between clear blue skies and bright cloud layers, creating smooth, gradual shifts in brightness. The distribution of water vapor is uneven, changing with weather patterns, seasons, and geography. Tropical regions typically show stronger softening effects, while dry deserts reveal sharper blue tones. This variation adds texture to the way Earth appears from orbit. Some regions glow with deep blue clarity, while others look gentle and subdued. Although water vapor does not define Earth's blue color, it fine-tunes it. It adjusts the brightness and smoothness of scattered light, giving the planet a calm, slightly diffused glow. In this way, water vapor acts like a natural lens, quietly shaping the look of Earth's atmosphere without drawing attention to itself. At the top and bottom of Earth lie two vast regions of ice, the Arctic and the Antarctic. These frozen landscapes are more than geographic features. They are powerful mirrors. Their bright surfaces reflect large amounts of sunlight back into space, helping to maintain the overall brightness of the planet. This reflective ability, known as albedo, makes the poles some of the most luminous areas on Earth when viewed from orbit. Fresh snow has one of the highest albedo values found in nature. It reflects most of the sunlight that reaches it, allowing very little to be absorbed. Ice is slightly less reflective than snow, but still bright enough to contribute to Earth's shine. Together, snow and ice create white caps that stand out clearly against the darker tones of oceans and land. Sunlight interacts with these icy surfaces in a simple but striking way. When light hits a snow-covered region, it bounces off in many directions. Unlike the selective scattering in the atmosphere, this reflection does not favor any particular wavelength. All visible colors are reflected almost evenly, which is why snow and ice appear white. From space, this reflected light forms large, radiant patches that anchor the planet's appearance. The shape and angle of the poles also influence how bright they appear. Because the sun stays low on the horizon in polar regions, its light grazes the ice at shallow angles. This geometry increases the amount of light reflected outward, making the poles glow strongly when Earth is seen from a distance. During polar summer, when the sun never fully sets, the effect becomes even more pronounced. These bright caps also vary with the seasons. In winter, polar ice expands and reflects even more sunlight. In summer, parts of the ice melt, revealing darker surfaces that absorb more light. These seasonal changes subtly alter Earth's global brightness. From space, satellites detect these fluctuations as shifts in the planet's overall reflectivity. The poles do more than reflect sunlight, they balance Earth's visual texture. The deep blues of the oceans, the gentle scatter of the atmosphere, and the brilliant whites of the ice create a layered, dynamic appearance. This contrast highlights the planet's complexity. It shows that Earth's blue glow is not uniform, but shaped by a combination of scattering, absorption, and reflection. The polar regions remind us that Earth's color is tied to its climate. Their brightness depends on temperature, weather patterns, and long-term environmental changes. As sunlight meets these icy surfaces, the planet broadcasts a clear message into space, a signal of cold, reflective boundaries that help define Earth's luminous identity. Earth's blue glow is more than a visual signature. It reflects the presence of an atmosphere, oceans, and a stable supply of sunlight conditions that together create a home for life. The color we see from space is a quiet indicator of the environmental balance that allows countless species to exist. In this way, Earth's blueness is not just an appearance, but a sign of habitability. The atmosphere plays the first essential role. Its scattering of sunlight creates a gentle, filtered illumination that softens the intensity of direct radiation. This scattered light stabilizes surface temperature and provides a protective layer that helps life develop without the constant threat of harmful radiation. The same scattering that colors the sky also diffuses sunlight, preventing extreme heat from concentrating in a single place. The oceans provide the second major ingredient. Water rocks as a cradle for early life, supporting chemical reactions that would not occur in a dry environment. Its ability to absorb and redistribute heat helps regulate the planet's climate. As sunlight penetrates the ocean, blue wavelengths travel deeper, creating a layered world of light that once sheltered the earliest living organisms. The color of the sea becomes a record of the conditions that shaped life's beginning. Earth's reflective clouds and ice caps add another layer of support. They help maintain the planet's energy balance by returning some sunlight to space. This balance prevents the surface from overheating and ensures stable conditions for ecosystems to grow. The interplay among air, water, and ice supports a climate that is neither too hot nor too cold. From space, the blue color tells a story. Planets with thick atmospheres or abundant water often display distinctive hues. Earth's particular shade, soft, luminous, and wrapped in white clouds, reveals the presence of all three life-supporting ingredients: air, water, and moderate temperature. Although life is not visible directly from orbit, the planet's appearance provides clues about the processes that sustain it. The connection between color and habitability is subtle but important. Earth's blue glow is not merely decorative. It is a signal that the planet has an atmosphere capable of scattering sunlight, oceans deep enough to absorb and reflect blue wavelengths, and a temperature range that keeps water in liquid form. These conditions together make Earth a seedbed for life. In this sense, the blue planet reminds us that life and environment are deeply intertwined. The color that defines Earth from afar is the result of the same physical processes that allow life to flourish on its surface. The glow carries a message. Where light meets air and water in balance, life can begin and grow. Earth's blue atmosphere does more than scatter sunlight. It acts as a shield, protecting life from radiation that would otherwise make the planet uninhabitable. The same molecules that give the sky its color, nitrogen, oxygen, and traces of ozone, shape the flow of energy reaching the surface. Their combined effects create a safe environment where life can survive and evolve. When sunlight reaches Earth, it arrives with a wide spectrum of energy. Some of this energy is harmless visible light, but other parts of the spectrum contain ultraviolet radiation, which can damage DNA and break apart fragile molecules. Without protection, these high-energy wavelengths would overwhelm Earth's surface. Instead, the atmosphere absorbs and scatters them before they reach the ground. Ozone plays the most direct role. It forms a thin layer high in the stratosphere, where it absorbs much of the sun's ultraviolet light. This absorption is not visible to the human eye, but its effect is enormous. It prevents the most harmful UV radiation from reaching the ground, reducing exposure to levels that life can tolerate. This layer is fragile, but even in its thinness, it performs one of the most important protective functions on the planet. Oxygen and nitrogen also contribute. Although they do not absorb UV radiation as strongly as ozone, they scatter high-energy wavelengths, redirecting them and spreading their energy over a wider region. This scattering weakens the intensity that reaches the surface. It also transforms dangerous radiation into the diffused light that fills the daytime sky. The blue glow we associate with Earth is partly a byproduct of this protection. Rayleigh scattering, which favors short wavelengths, removes a portion of the sun's high-energy light before it can reach the ground. The result is a softened, filtered illumination that allows life to exist comfortably. It is a natural light diffuser on a planetary scale. From space, the atmosphere's protective effect is not visible directly, but the thin blue line tracing Earth's curve hints at its presence. That narrow band contains the molecules responsible for absorbing, scattering, and transforming sunlight. Astronomers often describe it as delicate, so thin that it looks almost breakable, yet it performs a function vital to every organism on Earth. The relationship between protection and color reveals a deep connection. The same physical processes that shape Earth's blue appearance also guard the planet from harm. Light meets air, energy meets molecules, and the result is both beauty and safety. In the quiet glow of the atmosphere lies a shield that has allowed life to flourish for billions of years. Long before humans traveled into space, they looked up at the sky and noticed the color that defined their world. The blue dome overhead became a reference point for navigation, timekeeping, and early astronomy. The same scattering that colors Earth today shaped ancient observations and helped civilizations understand their place beneath the sky. Sailors were among the first to rely on the sky's color as a guide. A clear blue sky signaled stable weather and predictable winds, while a pale or hazy sky warned of distant storms or shifting air. The color of the atmosphere became part of practical navigation, a silent indicator woven into daily survival. Even without understanding Rayleigh scattering, early navigators sensed that the sky's hue carried information about the world around them. Astronomers, too, learned to read the atmosphere. They noticed how the sky brightened during the day, dimmed near twilight, and shifted colors with the angle of the sunday. These patterns revealed the presence of an atmosphere long before anyone knew its composition. The contrast between Earth's blue sky and the night's dark emptiness gave observers a sense of the planet's boundaries, an unseen shield separating life from space. As telescopes improved, astronomers began comparing Earth to other worlds. Mars appeared red, Venus pale yellow, and Jupiter streaked with bands. Earth, with its deep oceans and bright clouds, stood out as the only planet glowing blue. This comparison strengthened the idea that Earth was unique, a world shaped by water and air. Its color became shorthand for its identity, the blue planet. With the arrival of spaceflight, humanity finally saw Earth from above. The view confirmed what earlier observations had hinted at. The planet was wrapped in a thin blue halo, glowing softly against the darkness. Photographs taken during the early missions transformed scientific understanding and public imagination. The blue edge was no longer an abstract idea, but a visible marker of the atmosphere that sustains life. Astronauts often describe Earth's color as calming, fragile, and full of contrast, a world that seems both strong and delicate. From orbit, the blue is not just a color, but a sign of home. It distinguishes Earth from every other object in view, grounding human identity even in the vastness of space. Through navigation, astronomy, and exploration, the blue appearance of Earth has shaped how humans understand their planet. It is a signal of water, air, and life, a visual reminder of the environment that supports civilization. The color that fills the sky and outlines the horizon becomes, from a distance, the symbol of Earth itself. Asterisk, asterisk. Part 3, Subtopic 14, The Emotional Impact of the Blue Planet on Human Culture. Asterisk, asterisk. Earth's blue glow has shaped more than scientific understanding. It has influenced human emotion, imagination, and cultural identity. The sight of the sky, the color of the sea, and the image of Earth from space have become symbols that carry meaning beyond physics. The planet's blue appearance has quietly woven itself into art, literature, and the way people think about home. For early cultures, the blue sky was a source of wonder. It created a sense of openness, a vast ceiling that felt protective yet mysterious. Many mythologies describe the sky as a dome, a river, or a spiritual boundary. Its color inspired beliefs about the heavens and shaped ideas of where humans belonged in the universe. Even without knowing the science behind it, people felt a connection to the calmness of the blue horizon. The oceans deepened this emotional link. Their shifting shades of blue light near the shore, darker in the open sea, created feelings of depth, movement, and possibility. Across cultures, the sea became a symbol of exploration and introspection. Sailors, poets, and travelers often used its color to describe longing, discovery, and the quiet pull of distant places. The blue of water and the blue of the sky formed a continuous backdrop for human stories. When humans first saw Earth from space, the effect was transformative. The planet appeared as a small, radiant sphere wrapped in blue light. This perspective, later called the overview effect, stirred emotions that astronauts struggled to put into words. Many described feelings of unity, fragility, and responsibility. The thin blue line outlining Earth became a symbol of the delicate balance that supports life. Art and media embraced this imagery. Earth's blue color became a universal icon representing life, peace, and environmental awareness. Posters, photographs, and films used it to communicate the idea of a shared home. The image of the blue planet encouraged new cultural movements centered on ecology and planetary care. The connection between color and meaning grew stronger with each generation. Even today, the color blue shapes emotional responses to the natural world. A clear sky can bring calmness. A bright ocean view can evoke clarity or introspection. These reactions tie back to the physical reality of sunlight scattering through air and water. But they live on as emotional interpretations that differ from person to person. Earth's blue appearance shows how physical phenomena can influence culture. The scattered light that colors the sky and sea becomes part of human identity, shaping stories, art, and collective memory. In the planet's glow lies a shared sense of belonging, carried quietly through generations. Modern satellites allow us to observe Earth's blue glow with clarity that earlier generations could only imagine. These instruments orbit high above the surface, collecting data about how sunlight interacts with the atmosphere, oceans, clouds, and ice. Their measurements reveal the precise factors that shape the planet's appearance, turning Earth's color into a source of scientific information. Many satellites carry radiometers, sensors, that measure the intensity of light at different wavelengths. By detecting how much blue, green, and red light is reflected or scattered, these instruments create detailed maps of Earth's brightness. They can distinguish between areas where the atmosphere scatters light strongly and regions where the surface reflects more intensely. This data helps scientists understand how Earth's glow changes with seasons, weather, and climate. Imaging satellites provide another perspective. They capture photographs of Earth's surface and atmosphere across visible and infrared wavelengths. These images reveal the thin blue arc that outlines the planet, the shifting patterns of clouds, and the deep blues of the oceans. When viewed frame by frame, they show how Earth's appearance changes over time, sometimes subtly, sometimes dramatically. Other satellites specialize in atmospheric study. Instruments like spectrometers break sunlight into its component wavelengths to identify which gases are present and how they affect light. By analyzing these patterns, scientists can measure ozone levels, aerosol concentrations, and humidity. Each of these factors influences the brightness and color of Earth's atmosphere. Satellite data also tells us how reflective Earth is as a whole. By calculating the planet's albedo, researchers track how much sunlight is returned to space and how much is absorbed. Variations in albedo help scientists understand long-term climate trends, such as the melting of polar ice or changes in cloud cover. These measurements reveal how Earth's glow is linked to its energy balance and environmental health. From orbit, satellites see Earth as a dynamic, ever-changing sphere. Its color brightens when clouds spread, softens during dust storms, and deepens when the oceans come into full sunlight. By combining millions of observations, researchers build a complete picture of the processes that shape Earth's blue identity. Technology has transformed the way we understand the planet's appearance. What was once a visual impression, Earth as the blue planet, is now a measurable, trackable phenomenon. The glow seen from space becomes a scientific tool, offering insight into the atmosphere, climate, and environment. Through these instruments, Earth's light becomes both a symbol of beauty and a source of knowledge. Earth's blue glow feels timeless from our perspective, but like everything in the cosmos, it is shaped by conditions that can change. The atmosphere, oceans, and climate all contribute to the planet's color. As these elements evolve over millions or billions of years, Earth's appearance will slowly shift as well. The blue world we know today is one chapter in a much longer planetary story. The first factor that may change Earth's color is the atmosphere. Its composition has already transformed dramatically over the planet's history. Early Earth likely had a hazy, reddish sky dominated by volcanic gases. Only after oxygen became abundant did Rayleigh scattering create a clear blue. In the far future, atmospheric gases may shift again. If oxygen levels drop, or if new gases accumulate, the balance of scattering could change, making the sky appear paler, whiter, or even more muted. The oceans also play a key role. As long as liquid water covers most of the surface, Earth will retain much of its blue identity. But the sun is slowly brightening over time. In about a billion years, increased solar energy may cause large portions of the oceans to evaporate. With less water to absorb and reflect blue wavelengths, Earth's color could shift toward brown or beige, resembling drier planets like Mars. Clouds and ice will evolve as well. Expanding ice sheets could brighten the planet, giving it a whiter appearance. Conversely, if global temperatures rise and polar ice declines, Earth's albedo would drop, making the planet darker. These changes would be gradual, unfolding over long timescales, but they would subtly alter the glow seen from space. Another influence comes from aerosols and life itself. The presence or absence of vegetation, plankton, and biological activity affects the color of land and sea. A planet rich with life often displays more vibrant hues. If Earth's ecosystems transform or decline, the surface may lose some of its variation in color, softening the contrast between land and water. The most dramatic changes will happen in the distant future, when the sun enters its red giant phase. As the sun expands and heats the planet, Earth will lose its oceans and atmosphere entirely. Without air to scatter light or water to reflect blue wavelengths, the planet will no longer shine as a blue world. It will become a bare, rocky sphere, silent, dim, and colorless against the bright red star it once orbited. From a cosmic perspective, Earth's blue color is temporary. Yet for now, the balance of air, water, and sunlight continues to shape a world defined by its gentle glow. The blue we see today is a reflection of present conditions, a sign that Earth is still alive, temperate, and full of movement. Its color is both a product of physics and a moment in time, a reminder that even familiar sights are part of an ever. Earth is often called the blue planet, but it is not the only object in the cosmos that shines with shades of blue. Other planets, moons, and even stars display blue hues for completely different reasons. Comparing Earth with these worlds helps reveal what makes its color unique and what it shares with the broader universe. Some planets appear blue because of the gases in their atmospheres. Neptune and Uranus, for example, have methane-rich atmospheres that absorb red wavelengths and reflect blue ones. Their color comes not from scattering, as on Earth, but from selective absorption. The blue of Neptune is deeper and more vivid, almost electric, because the methane absorbs so much red light. Seen from afar, these planets shine with a colder, more intense blue than Earth's soft glow. Other worlds appear blue for geological reasons. Some icy moons, like Enceladus, reflect sunlight off surfaces of ice crystals that scatter blue wavelengths more effectively than red. In these cases, the blue color has nothing to do with an atmosphere. It originates from the way ice grains handle light. These moons have a crisp, icy brightness that differs from Earth's atmospheric haze. Even stars can appear blue. Hot, massive stars emit most of their light at short wavelengths, giving them a bright blue-white color. This is not scattering or reflection, but thermal radiation. Their surfaces are thousands of degrees hotter than the sun, causing them to glow with an intense blue brilliance. Compared to these stars, Earth's color is gentle and pale, shaped by the interplay of light with air and water rather than by extreme heat. A few exoplanets' worlds orbiting other stars also show evidence of blue colors. One example is HD 189733b, a gas giant with an atmosphere filled with silicate particles. These particles scatter blue light, giving the planet a deep cobalt tone, but the environment beneath that color is violent and hot, with winds faster than any on Earth. The beauty of the blue hides a world entirely different from our own. These comparisons highlight what makes Earth special. Its blue is not the result of extreme temperatures, exotic gases, or mineral surfaces. Instead, it comes from a balanced combination of a breathable atmosphere, liquid water, and mild sunlight conditions that support life. Earth's blue is a living blue, shaped by processes that also sustain oceans, weather, and ecosystems. Across the universe, many objects appear blue, but each tells a different story. Earth's version is quiet, stable, and connected to life. When compared with other blue worlds, our planet stands out as a place where gentle scattering, calm oceans, and reflective clouds create a color that signals not only beauty, but habitability. If an alien civilization were to observe Earth from across the cosmos, the planet's blue glow would be one of the first clues that something unusual was happening here. From a distance, Earth would not look like a barren rock or a gas giant. Instead, it would appear as a small world wrapped in a thin, luminous shell of blue, a color that hints at air, water, and the possibility of life. An alien astronomer, using instruments similar to our own telescopes, would analyze the light reflected from Earth. They would notice that the planet scatters short wavelengths strongly, producing a soft blue signal. This pattern would suggest the presence of a clear atmosphere dominated by lightweight molecules like nitrogen and oxygen. Such a composition is rare among the planets we have discovered. To a distant observer, it would mark Earth as an outlier. They might also detect the bright white flashes of clouds drifting across the surface. These clouds would reveal active weather systems and a constantly changing climate signs that the atmosphere is dynamic rather than static. The contrast between deep blue oceans and reflective cloud tops would produce variations in brightness as the planet rotates. Over time, these variations would form a repeating rhythm, revealing the length of Earth's day. The oceans themselves would offer another clue. The way Earth absorbs long wavelengths and reflects short ones would point toward the presence of liquid water. For an alien civilization familiar with the physics of light, this pattern would be unmistakable. Water has a distinctive spectral fingerprint, and the blue tone produced by vast seas would stand out clearly against the darkness of space. If they observed Earth over weeks or months, they might notice seasonal shifts, the tilt of the planet, expressed through changing patterns of snow, ice, and vegetation. The growth and retreat of polar caps, the brightening of clouds, and the darkening of land would form a cycle that repeats every year. These signals would reveal that Earth is not just blue, but alive with motion. More advanced instruments could search for atmospheric gases like oxygen, carbon dioxide, and methane. The combination of these gases in specific ratios would suggest biological activity. To an alien scientist, this mixture would be a strong hint that some form of life is actively shaping the planet's atmosphere. From their perspective, Earth's blue glow would not simply be a color. It would be a message encoded in light evidence of an atmosphere that scatters, oceans that reflect, and ecosystems that breathe. The planet would stand out as a place where energy, matter, and life interact in a delicate balance. To an observer across the galaxy, Earth would shine as a small, steady beacon of blue, quiet but unmistakable, signaling that something rare is happening on this world. A planet where light, air, and water combine to support life. In the search for life beyond Earth, color can be more than a visual detail. It can be a scientific clue. When astronomers study distant planets, they look for patterns in reflected light that hint at atmospheric composition, surface features, and environmental stability. Earth's blue glow serves as a powerful example of how a planet's color can reveal the presence of conditions that support life. Blue light scattered by a clear atmosphere suggests that the planet contains gases capable of filtering sunlight without blocking it entirely. On Earth, this balance is achieved through nitrogen, oxygen, and trace amounts of other molecules. These gases indicate not only stability, but also chemical processes that may be influenced by living organisms. Oxygen, in particular, is a strong biosignature, a sign that photosynthetic life helps maintain the atmosphere. The combination of blue scattering and white cloud reflectivity forms a pattern that astronomers can detect even from great distances. Clouds suggest an active water cycle. A water cycle implies oceans, evaporation, and rainfall systems that regulate temperature and support complex ecosystems. The simultaneous presence of blue light and cloud reflection can signal a world with both air and liquid water, two major ingredients for life as we know it. In the field of astrobiology, researchers study how different wavelengths of light reflect off various planetary surfaces. Blue signatures may indicate oceans, ice, or clear atmospheres, depending on context. But when these features appear together, deep blue tones, bright cloud patches, and spectral hints of oxygen, the combination becomes complete. It points toward a planet that is not only habitable, but potentially inhabited. Earth provides the template for interpreting these signals. When scientists examine exoplanets, they often compare their light curves to Earth's. Variations in brightness as a planet rotates can reveal the contrast between land, water, and clouds. If another world displayed patterns similar to Earth's, it would immediately rise to the top of the list for potential life. However, blue alone is not enough. Some planets appear blue for reasons unrelated to life, such as methane absorption or reflective ice. The true signature lies in how different signals combine. A planet's color must align with atmospheric chemistry, thermal behavior, and orbital conditions to form a consistent picture. Only then can scientists reasonably suspect that that life might exist. In this sense, Earth's blue glow is both a symbol and a guide. It shows how light interacts with a living planet and how life leaves subtle fingerprints on the spectrum of reflected light. When astronomers scan the galaxy, they look for worlds shaped. From a distance, Earth appears as a small sphere wrapped in a thin halo of blue. The color is gentle, almost fragile, yet unmistakable against the darkness of space. This glow is created by simple physics, sunlight scattering in air and reflecting from oceans, but its meaning reaches far beyond the science alone. Earth's blue light invites reflection on what it means to live on this planet and how it fits within the vast universe. The thin atmosphere responsible for this glow is a reminder of how delicate Earth truly is. It contains all the air that humans, animals, and plants depend on. When seen from orbit, the atmosphere looks almost impossibly narrow, like a thin veil stretched over the surface. Its presence shows that life is supported not by a thick shell or an unbreakable shield, but by a faint whisper of gases that interact with sunlight. The oceans add depth to this picture. Their blue color comes from the way water absorbs and scatters light, but the meaning behind it is larger. Oceans regulate climate, cradle ecosystems, and connect every continent. They tie the planet together in a continuous cycle of evaporation, clouds, and rain. The blue of the sea echoes the blue of the sky, forming a single visual thread linking air and water, surface, and atmosphere. The clouds, snow, and ice that brighten Earth remind us that the planet is active and dynamic. They shift and reform, balancing temperature and reflecting sunlight. From above, these bright patches appear almost like breathing, expanding, thinning, and returning again. They show that Earth is not static, but alive with movement on every scale. Seen from afar, Earth's glow makes clear how small we are in comparison to the universe. Stars, nebulae, and galaxies shine with their own light, powered by nuclear fusion or illuminated by enormous clouds of dust. Earth's light, by contrast, is quiet and reflected, shaped by the meeting of sunlight with a planet that hosts life. Its glow is not the light of a star, but the light of a world that supports oceans, weather, forests, and minds capable of reflection. This contrast gives Earth's blue halo a symbolic weight. It reminds us that life is rare in the cosmic landscape. It suggests that the conditions allowing us to exist are the result of a delicate balance: air of the right density, water in the right form, and sunlight of the right intensity. The blue glow becomes a visual expression of that balance, a sign that the planet is neither too hot nor too cold, neither bare nor chaotic. In the quiet light surrounding Earth, we can see the story of a planet shaped by time, physics, and the presence of life. It is a reminder of connection between humans and their world, between light and atmosphere, and between a small blue sphere and a universe full of distant suns. The glow tells us that even in a vast cosmos, there are places where conditions align to create life, and that Earth is one of them.